Hello everyone, welcome to my YouTube channel. In a previous video lecture, we have seen how to calculate the magnetic field intensity by using the vector formula. In today's video lecture, we will discuss about the Ampere circuital law, and after that we will see Stokes theorem. Okay, so let us start with the first point, that is Ampere's circuital law. This law is also called as Ampere's work law. We can say this as also Ampere work law. Okay, so let us see first the statement of this Ampere circuital law. It states that the line integral of magnetic field intensity. We know that the magnetic field intensity is denoted by h bar. So we can write here the line integral of magnetic field intensity, that is h bar, about any closed path. Means what? Here the path should be closed, which is exactly equal to the direct current enclosed by that path. That is nothing but capital I. Okay, so here we can say that this line integral is the closed path integration, or we can say line integration, which is denoted by this symbol. Then h bar is the magnetic field intensity. Then dl is the small differential length with respect to h bar, and I is the current enclosed by the given path. Okay, so let us see how to prove this equation or this statement. For this, we have to consider this long straight conductor. This is the long straight conductor which consisting of current. So here the long straight conductor carrying current I, as shown in this figure. So as shown in this figure, we can say the magnetic flux density is along the circular path like this. It will move like this. That is nothing but B bar. This is the magnetic field intensity. It is a magnetic flux density. Then now at a distance of r from this conductor, this is the origin and this is the capital R. That is the distance from the conductor and the magnetic flux density, which is already given by the Biot-Savart's law. We know that the statement of Biot-Savart's law is B is equal to mu I divided by 2 pi r. This is the statement of Biot-Savart's law. In that we have seen this mu is nothing but what? This is the permeability of medium. That mu is also write as a mu 0 into mu r. Okay, then I is the current passing through that conductor. This is the conductor and this current I is passing through this conductor, and r is the radius of the circular path. Okay, now after that we will integrate this B bar around the path of radius r, including the wire, which is denoted by this BDL bar. Okay, so again this question is that how to decide the direction of B and this DL bar. So let us consider the conductor, that is wire, which carrying current I. So we have to use the cylindrical coordinate system. Okay, as we know that the coordinates in cylindrical coordinate systems are r into dr. This is r, that is nothing but dr. Then phi as a r into d phi, and z is the dz. Okay, so these are the coordinates in cylindrical coordinate system. R as a dr, then phi, this is phi as r into d phi, and z is dz. Okay, so here r is the radius and radius of circular path of B bar is constant. So we can write dr is equal to 0. Why? Because this is constant value. Then second is the B bar, that is rotating around the conductor. So it is represented by the angle phi. So the direction of B is what? This is A phi bar. Okay, and then again there is a z parameter, that is constant plane, so we can directly take the value of dz is equal to 0. Okay. Then we are taking again the dot product of b into dl bar. Why? Because here we have to take dot product of this b and dl bar. So here the direction of b bar is a phi bar, so the direction of this dl bar must be a phi bar, because the dot product of this two similar unit vector is 1 and two dissimilar unit vector will be 0. Okay. So here this dl bar is equal to dl into a phi bar. Okay, because here we are going to take the dot product of two similar unit vectors, so we have to take with respect to a phi bar. Okay, so here we'll get integration of line integral of this b into dl bar is equal to line integral of this b bar with respect to a phi bar into again dl bar into with respect to a phi bar. Okay, so here combinedly we'll get the line integral of b dl in bracket a phi bar dot a phi bar. Okay, so here we know that the dot product of these two similar unit vectors should be 1, that is a phi bar dot a phi bar is equal to 1. So we can write this left hand side as it is, that is integral line integral of b bar dot dl bar is equal to right hand side right integral of b into dl bar. Okay, so here again we can write this in the form of integration. So we can write integration of b bar into dl bar is equal to b into line integral of dl bar or dl bar. So we know that this differential length is nothing but total length, that is the length of circular path, and here we have denoted this circular path using this r, and this r is consisting of the circular path, so that's why we can take direct the circumference of this circle, that is equal to 2 pi r. So we can write here the left hand side again as it is, this equation line integral of b bar dot dl bar is equal to the value of this b should be the same, and the value of this line integral of dl bar is equal to 2 pi r. Okay, then in a second equation we can see here again the left hand side equation will be the same. This is the same equation. Then at right hand side b into 2 pi r is there, and according to the Biot-Savart's law we know that the value of b is equal to mu I upon 2 pi r. So we can directly put this value of b into this equation, that is equal to mu I upon 2 pi r into again this 2 pi r as it is. So this 2 pi r and this 2 pi r become cancel. So we'll get line integral of b bar into dl bar is equal to mu I. So if we divide this equation by mu, means what, we have to just shift this mu to the left hand side, so it will become line integral of b bar upon mu into dl bar as it is equal to capital I, that is total current. So here we have one relation, that is b is equal to mu into h bar. So we can write here in terms of magnetic field intensity. So here this b bar is equal to mu h bar, then this numerator mu and denominator mu get cancelled, so the remaining equation is line integral of h bar into dl bar is equal to I. That is our final statement for the Ampere circuital law. Okay, so we know that according to Ampere circuital law, the current enclosed by the closed path is equal to line integral of h into dl bar. Hence it is proved. Okay, so usually this equation is used to calculate the equation of this h bar, now which is provided the current when the current I is known. So in this way we have studied the Ampere circuital law statement and its proof. Next point is to study applications of Ampere circuital law. So we have seen that equation, in that we have calculated the value of magnetic field intensity. So that's why this law, that is Ampere circuital law, can be used to find magnetic field intensity due to the long straight filament, or we can also calculate the magnetic field intensity, that is H bar, due to the coaxial cable. Okay, so these are some applications of Ampere circuital law. Then next point we are going to study here the physical significance of curl. CURL, that is curl. So here let us see what is the significance of this curl. So physically the curl, it is the measure of tendency of a vector to curl or to cause rotation or twisting. Let us see one example. Consider that a child has launched a tiny paper boat at this point P. This is boat and this is point P in a flowing stream of water near the bank. This is the bank and this is the tiny paper boat at point P. Okay, so here this situation we can see in this figure. So first of all, this paper boat moves along this y direction. This is x, this is y, and this is z direction. So this boat will move along this y direction. Then at a point P, this is point P, the velocity of water is denoted by Vy, that is which will move along with the y direction. So that's why we can consider as a Vy. So as we move inside the water, what happened? Away from the bank, then the velocity increases. Here the bank is there and the velocity is here. So if we move away from the bank, then the velocity increases. That means velocity increases as x increases. So at point P, velocity Vy cause the motion of a boat that is parallel to this y-axis. Okay, so now at a distance dx from point P, this is the P and this is the distance of dx. The velocity is what? Vy plus del Vy upon del x with respect to dx, because velocity is changing with respect to x. Okay, so here it indicates that the value of velocity at opposite sides of point P are not equal. So this causes the rotation of boat about this point P along the direction which can be shown in this figure. So this indicates the curl operation, that is which cause the rotation or the twisting. So according to the definition of curl, we can write the curl of V bar is equal to del into V bar. So here we can write the value of del is equal to, in matrix form, Ax bar, Ay bar, Az bar. With respect to Ax bar, dou by dou x, then dou by dou y, then dou by dou z upon this Vx, Vy and Vz. Okay, so this is a 3 by 3 matrix where we can put the coordinates of x, y, z. With respect to x, y, z, we can write dou by dou values, and here we have to take curl of V bar. So here we can write the values of V, that is Vx, Vy, Vz along with the x, y, z direction. Okay, so here in this case the velocity of water is Vy and it is changing with x. So thus this Vx and Vz becomes 0. Why? Because here we have to take Vy along with the y direction. Okay, so that's why the z and y velocity components becomes 0. So we can write here del into V bar is equal to del upon del x into Vy into Az bar. Okay, so note that in this case the rotation of boat, or we can say the curl, is obtained only because of unequal velocities at both sides of point P. Next point is Stokes theorem. So again, in terms of Stokes theorem, we will see first statement of the Stokes theorem, and after that we will see the proof of that theorem. Okay, so let us see first the statement. So here the statement of Stokes theorem is that the integration of any vector around the closed path is always equal to the integration of curl of that vector throughout the surface enclosed by that path. Okay, so let us see first how to prove that statement. For that we have to consider a surface S which is broken into the incremental surface del S. So here we can see this is the closed broken surface S, and here this del S is the incremental surfaces. Okay, so here this each incremental area of this del S is tends to 0. So we can say that according to the Ampere circuital law, the current enclosed by the closed surface is H dl is equal to I. We have already studied this statement, that is Ampere circuital law. The line integral of this H bar into dl bar is equal to I. Then this current can be expressed as the surface integration of current density over the closed surface also. That means we can write here in terms of current density, and we know that current density is J is equal to I divided by A is there, means current flowing through per unit area is nothing but current density. Okay, so here we can write this I bar is equal to J bar into ds bar in terms of the current density. Okay, so here the left hand side is what? Here H bar dl bar is as it is equal to the value of I is equal to J into this area, or we can say J into surface area. So we can write this, the value of this right hand side of I as a integration over the closed surface S inside integration J bar into ds bar using these two equations. Okay, so here according to the point form of Ampere's law, we have this statement, that is del into H bar is equal to J. Here this is the constant value of this J bar according to the Ampere's law, or we can say the point form of the Ampere's law. Okay, remember this equation. Then we have to just put this equation into the previous one. So we'll get integration over the closed surface, or the line integral of H bar into dl bar, that is left hand side is as it is equal to integration over closed surface. The value of J is del into H bar, and the value of this ds bar is as it is. So we can put here del into H bar into ds bar. Okay, so this is the final statement of the Stokes theorem. The statement of Stokes theorem is the integration of any vector, this is integration of any vector around the closed path. Here remember one point, the path should be closed. That closed path vector is always equal to the integration of this curl. We know that the curl means we have to just take cross product of del with that parameter. So here as a left hand side we have to consider the magnetic field intensity. So in similar way at the right hand side we have to take the curl of that given parameter throughout the surface enclosed by that path. That's why we have to consider the surface area also. Okay, so here this equation indicates that the del into H bar is the curl of H bar. Whenever we are going to calculate the curl of any parameter, we have to just take cross product of that given term into the del. Okay, so this equation, using this equation we can conclude that the line integral of any vector, so here suppose H bar is there, H bar vector is there, so the line integral of this H bar is always equal to the surface integral of a curl of that vector over the surface enclosed by that path. This is the statement and proof of the Stokes theorem. So this is all about our today's session. I hope you will like and enjoy. We will stop here with motivational quote. Today's motivational quote for you is, the best project you will ever work on is you. Thank you for watching my videos. Please like, share and subscribe to my channel. Thank you so much.